And I'm recording this. Okay, so today we're going to go through examples of implementing these various classification techniques. Just to refresh your brain for a second, classification is just like regression, except we have a discrete outcome, typically two classes. So you treat them as zeros and ones, and there's different ways to visualize and think about classification. Then we went over various types of classification, including logistic regression, LDA, SVM, and these nearest neighbor techniques. And at some level, they're all the same if they're all linear, because it's all a matter of finding a line that separates our classes. So in these examples that we're going to do, I go through two examples here. Let me just do that really quickly, and we'll go through some exercises. These two examples, let's see, the first one focuses on logistic regression, which is just one specific flavor of a classifier, and the other example kind of shows you how to implement multiple different classifiers on this exact same data set, just as sort of a demonstration. So first we'll generate some fake data. So what we're doing here, our usual random statement. So now we have some random dots that we're going to visualize in a second, and we're going to associate basically a class 0, 1 with each dot. So each dot could be like a subject. We measured two properties for each subject, and my y variable will contain the classification outcome for that subject. And here it was just obtained using, if you notice, a linear combination of my two regressors, 2x plus 2x1 plus x2. And then we're just going to add some noise on top of that just to make it a little more interesting. And we're going to threshold it based on some value here, 1, and that just converts everything to zeros and ones. So if you just look at y, it's a bunch of zeros and ones, and we have 50 subjects, so it's a 50 by 1 vector. So that generated some classification type data, and we can do a quick visualization. We're going to open up our figure, and we're going to draw this plot where the first time we'll just select out all the data points labeled 0. So if you just do this logical operation, whenever y equals 0, that's going to give us a vector of indices. So it'll actually put a 1 wherever that's true. So we're going to select all the 0 points and then put up a dot at the appropriate x1 and x2 location and color it black. And we're going to, this is the size parameter. It makes the dot actually have some width here. And k means black, and filled just means fill it with black. So that's one class of subjects, and the other class is just do the exact same thing, but using the logical operation against class 1. And so notice they're invisible. Actually, you can't notice they're invisible. And so what I do here is, given the plot handles of each plot operation generates these handles, right? These are little numbers referring to the things that we just drew. We can say, set this property of them to be gray. So the edge of each dot will now be in between. So this is RGB, if you remember. Ranges from 0 to 1, so right in the middle is gray. So now we can see all our subjects, and we should label stuff. So we have our handles, so we can of course use them to put up a little legend very easily. Let's just label the axes. So for each subject, we're plotting their measured x1 and x2 values, and we're indicating using color their class. So what we're doing here, this whole example, is trying to predict class assignment from the regressors that we start with, these x1 and x2. So and specifically, if we're going to use a linear classifier, and we are for this example, we're going to try to draw a line that separates black versus white. And you can see that I can kind of draw a line like that, and that should probably do a reasonably good job separating them. This figure isn't exactly like this, of course, because of the random, but the code will still work. So in this example, we're going to use a specific technique, logistic regression. In the lecture notes of the previous lecture, I go through some of the derivation of why this works, but essentially what we do is we're going to say that a linear combination of our regressors, so x1 and x2, and we're also going to include a constant regressor, so that's 3. We're going to use some linear combination of those regressors and then pass the output through the logistic function, which just squashes some real valued number into the range 0 to 1, and we're going to use that function as a model for the class, which is either 0 or 1. So to fit that model, in this example, we're going to use an optimization approach. So our usual optimization options that we'll define here. And now we got to kind of set up the model. So here I'm just going to write this function. It's an anonymous function that evaluates the logistic function. So it's just 1 divided by 1 plus e to the negative x, where x is the input into the function. So x can be negative infinity to infinity, but the output of this function ranges between 0 and 1. So that's the logistic function, and now we need to construct the regressors that will feed into this. So we'll just do it in the usual fashion. Capital X will be our 2 regressors that we were given with, so 50 subjects defined in 2 dimensions. We're going to add a constant column for the constant regressor, so now we have 3 regressors. Then we're going to define some parameter related stuff. We're going to start the search at some point. Let's just set it to all zeros, so the weight is 0, 0, 0 for each of our 3 regressors. We won't worry about setting bounds, so lower bound, upper bound, just leave it empty. And then if you remember, what we do when we do logistic regression is interpret. So we're not minimizing squared error, which would be the usual thing with regression and Gaussian noise, but here we're going to, similar to the Gaussian case and regression case, we're going to maximize the likelihood, which is the same as minimizing the negative log likelihood. And if we interpret the output of the logistic function as a probability, then that kind of, through some derivation, gives rise to this cost function. One small note is there's a EPS. So EPS means epsilon. It's just a very small number. And the reason we do that is because if you do log of 0, you get something that's not a finite number. But if you do a simple hack, like add a little bit, then you can take the log and it is an actual number. And we're going to use that just to avoid finite, infinite problems here. So, okay. So we set up all this setup stuff, and the final call will use the LSQ nonlinear function to find parameters that minimize this cost function, this negative log likelihood. So it's going to start at 0, 0, 0 for the 3 parameters, and it's just going to search through that space to minimize this. So we can do that. And I left the display option to iter, so every iteration is going to display something. So the relevant column, most relevant, is this column, and it tells us basically the cost function at each iteration. So notice it's going down, and it eventually finds what it believes to be a minimum. All right, so we have our parameters. We can just look at them really quick. So 3.2 times the first regressor x1 plus 1.8 times the second regressor x2 minus 0.7. That's a weight on the constant regressor. So that's the weighted sum that it determined, that when you pass it through the logistic, then that maximizes the likelihood of the data. So that's all fine and dandy, but let's visualize this to kind of check that it makes sense. So we're trying to predict y, remember. So y is the class assignment. So what is the predicted class assignment according to this model? Well, you just take your regressors, multiply it times the weights. So multiply these 2 matrices and pass it through the logistic function, and that will give you, let me actually just evaluate that, that'll give you numbers between 0 and 1 as we expect. But the final class prediction, what we do is we interpret it as relative to 0.5. So 0.5 is the cutoff. So if you're above 0.5, you're more likely to be in class 1. If you're below 0.5, you're more likely to be in class 0. So we just use this logical operation to convert that into a discrete outcome. So now we have 0s and 1s, and we can do percent correct. So out of all of our 50 subjects, our 50 subjects actual labels were y. Our model prediction is here. I guess that's not very useful. Let's do it like that, transpose it. That's still not useful. Actually, a scatter plot would also not be useful, because then you would just see, whoops, sorry about that. Then you just see that. You hit points in all 4 cases. That's not useful. What you could do, this is kind of a tangent, we could do something like an image, assuming I know how to construct. Oh, there you go. So now we have an image. Let's change the color map just so it's nicer. So black is 0, white is 1. The data is in the top row. Your model fit is on the bottom row. As you can see, there's a pretty good correspondence. You can, of course, check. You can flip a coin 50 times and see how ugly that looks. So you do something like that. And so for comparison, you do a figure like that. Whoops, color. Okay. So this is the random. So if you, well, actually, maybe it's, this looks a little better than that, but maybe by eye you can't tell that much. So that's, anyway, that's a tangent. But we can just do it quantitatively. So you just check, compare the two vectors. So you do this logical operation between the two vectors, and it will be 1 if and only if both are the same. So if one's 0 and the other 0, this will be true. If one is 1 and the other is also 1, this will be true. Anything else, it'll be 0. So this quantifies correctness. And then you just sum how many of the 50 subjects had correct matches. So 43 out of 50. Then how many?
You know why, like, this is assuming that you already know that it should be correctly classified, right?
Well, we started off with y, right? We're given 50 subjects that we've measured 2 different attributes on, and we know some y variable we're trying to predict. So we know y.
This is like training.
Yeah, this is totally training. We're not doing any sort of cross-validation or prediction or anything. So correct divided by the number of cases, which is just the length of y, the number of subjects, times 100. So 43 divided by 50 times 100, or just do it like that. So 86%. So that's good. And then the rest of this is just visualization. So, oh, unfortunately I closed my figure. So let's just plot it back up, close all. And then do some visualization down here. So here, oh, actually it's a little complicated, so let me go over it. So here I just get the axis range. So this, the first 2 are the range of the current plot of the x axis, -2 to 2, and also it's, I guess, it's -2 to 2.5 for the y, or this axis, and I use that, and I guess the goal of this next section is to visualize the surface, because the logistic function takes, before the logistic function, it's just a plane. We have 2 variables, so it's a 2-dimensional plane that's defined on these 2 variables. And then what the logistic function does is takes that plane and then squashes it, because the plane goes on to infinity and negative infinity. The logistic function takes that and maps it to being 0 and 1. So now you have this kind of a step. It's a smooth step. It goes for a while at 0, and then it goes up gradually to 1, and then it stays at 1. So we want to visualize that. So the idea here then is we're going to define a grid of points. So that plane we're going to visualize has a value for each point in this 2-dimensional space. So we're going to do a bunch of work to define some points. So this takes 100 points equally spaced in the x direction. So this goes from -2 to 2. We want 100 points in the y direction. So that goes from -2 to 2.5. And then we use this function. So let me just show you before this function, we just have our 100x values and 100y values, and this function kind of does the cross product of them in some sense. So let me just show you what that means. So now we have 2 matrices. Each matrix is 100 by 100, corresponding to our grid. We're making a grid, and each grid point has an x value and a y value. So let's just look at the first row of xx. Xx is the x coordinate. So for the first row of our grid, so you might imagine we're going along there and there and there and there. So we have 100 different points going along the upper part of this plot. And we want to know the x coordinates, and that's given by this. So it goes from -2 to 2, good. And then we want to know the y coordinate, so let's just look at those points. Oh, oops. It's actually the bottom row, sorry. So now the y coordinate for this first row is the y coordinate of the points going from here, here, here. So the y is always -2. So another way to think about it is, let's view xx and yy as images. So this color is annoying, so let's just think of it like that. So the xx matrix is literally like this. So if I were to type XX, you would, well, it's too many values, but there's a direct mapping. Like we're looking at the matrix as if you would look at it at your command window. You can see the X values go from -2 to 2 as expected. You can also look at your Y values, and hopefully this will make it clearer. Like so. The Y values are, again, 100 by 100, just like our X values, but they go upward. So, so they range from -2 to 2.5. Does that make some sense? So these XX and YY are just our grid that we're going to evaluate our final model fit on. So then to do that, we take all of our X values and make this regressor matrix out of them. Right, so again, we have 3 regressors, but now we have 10,000 different points that we're evaluating this function at. So all you do is take that, multiply times the parameters we found from our fitting, pass it through the logistic function, and then make it a square again. So this is just 100 by 100. And we can visualize this using image sc. So I just issued that command. So image sc treats this as just a 100 by 100 matrix, and so you see the range go from 1 to 100 and 1 to 100. We have to do one more step to kind of put it in the right spot, and that's this command. So we're going to take, we saved our figure handle, we're going to tell it that the x range of this image, so going in this direction, actually corresponds to these values we started off with, and the y range, so from 1 to 100, that should actually map onto the y values we defined up here. So once we do this, it just moves the image in the appropriate fashion on the axes. So now the axes are correct. And let's again change the color map. We don't like this color map. Okay, we changed the color map, put up a color bar. Now things are starting to make a little more sense. We're visualizing the output of the logistic function model, and it ranges between 0 and 1. And we're almost done. This might be a little confusing, sorry about that. The final decision boundary is the midpoint of this surface. So it's whenever it equals 0.5. And we can use a built-in visualization tool of MATLAB called Contour. I won't bother you with the details of that, but all this does is plots a line. I need to make the line different from the current color map so you can see it. So this makes it RGB, so it's blue. It's a thick blue line. So just Contour calculated the ISO contour on this surface and plots a little patch, in this case a straight line, matched to the 0.5 contour of this underlying surface. So that is the decision, the final decision boundary proffered by this logistic regression model. I couldn't think of a better word. Some final things. We can't see the dots, so we got to kind of move things around. You can look at the help for UI stack. So now we can actually see the dots. And image sc kind of put this extra white space. Let's just change the axes back to what it used to be. So we can use the axis command. Remember the axis was that. Finally. So now we see our original data, their class assignments, the underlying logistic regression surface, the 0.5 contour of that surface, and then you can sort of think about, did everything work? If you look at the blue line, is it separating the 2 points into 2 groups, and is the accuracy level actually something like 86%? Looks like it's right. Let's just put that in the title, and we're done. I know this little bit was probably a little confusing, but it'll take a little bit of thinking about to work that out, or we can do some additional examples. All right, let's go on to the second example. This was just one particular flavor of classifier. Oh, I'm not done. You can do a 3D, so surf is a MATLAB function. We're just going to do an alternative visualization of what we've already computed. So this output image, remember, was the output of the logistic regression model. And we're going to use surf to visualize it. And this actually shows you the 100 by 100 grid, but we don't like all those lines. So let's turn off the edges by making them transparent, except that they're not. Maybe it's an OpenGL problem. Hold on 1 second. Let me just see if this goes away. Oh, technical issues. Anyway, ignore the fact that it looks a little ugly. But as you can see, this kind of shows you the structure of that surface now in 3D. So you get the smoothly rising surface. Your x1 is here, your x2 is here, and then the y is sort of the output. Yeah, you can try this. I'm using an old school. I don't have the GUI on. I think that's the reason. But you can kind of see the structure here. Whoops. That's a little better. It should look like that. Okay, moving on to the second example. Alright, so let's generate some fake data. The format's a little different. I forget why. Being able to flexibly work with different data formats is a good idea. So here I have, what do I have? I have 100 subjects defined along 2 dimensions. Don't worry about what I specifically made them. And then we have a different set of subjects, or we believe a different set of subjects, and they have the same data. So every subject has 2 things measured for them, and we believe we have 2 groups, and we want to see how well we can separate out who's in what group, based on their 2 attributes. So to make a little more sense, as usual, look at your data, visualize your data. So we're going to do a scatter plot. So for the first group, we'll take their 2 attributes and just do a scatter plot and use black dots to indicate where all the subjects lie. So our first group of 100 subjects sort of lives in this part of the space. Then our second group lives in this other part. Let's use a white dot, which you can't see. So now we make it visible using a... Okay, so now here we have 200 subjects, and it looks like they're pretty well separated. In other words, you can classify a subject based on their values along the x1 and x2 dimensions. So then we just put up some labels, and it looks good. If only your data looked as good as this, huh? So, alright, so then we do some preparatory work, same as before. So use the axes to define a grid, and we do this mesh grid business. And I guess the end of this, we have our grid's a little finer, so a 200 by 200 grid is 40,000 points defined in 2 dimensions. So this dimension, the other dimension. We're going to use that later below. So below we have 3 different linear classifiers. So the first one is logistic. We actually just did logistics in an earlier example. But we're going to use a different implementation. glmfit is a built-in MATLAB function in the stats toolbox, I believe. We can do a quick check. Whoops. Yeah. Anyway, so this uses this particular implementation, or example here is using that. And you can read the documentation there, but it also does logistic regression. And so, of course, you got to get your data into the format it wants. And it's pretty straightforward. I won't bother you with the details here. So I set up capital X and Y in a certain fashion, and then give it to glmfit. So what it's going to do is spit out parameters as usual. So there's 3 parameters as we expected. Then we're going to use this corresponding function, evaluate this model, glmval, evaluate, using these parameters at our grid locations. So I'm glossing over some of the details, but basically the structure is what's important here. So we fit the model, now we're evaluating it over the grid that we defined up here, and we're going to just reshape that into a square and then put a contour at the 0.5 contour. And so once we do that, then we see the decision boundary associated with doing the logistic regression on these data. And we'll just make it a blue and thick line just so you can see it better. So that looks reasonable. But there are other classifiers we can apply. So linear discriminant analysis, if you remember, models each of these distributions and then generates the decision boundary based on that. Classify is a built-in MATLAB function. We'll just use that. Again, it has its own input and output format. But basically what's happening is this x and y we defined up here we're going to reuse, and what it does is does LDA to determine the parameters of the, it fits this multivariate Gaussian, and then it automatically evaluates at the first argument. So we're going to ask it, do your fitting on these data, and then evaluate at the grid, and then that's how we can get our output image. Then we'll just reshape it, and then again do the exact same thing we did up here, put a contour at the 0.5 line, oops, and then let's make it visible, so make that line green. So now we can see, according to LDA applied to the data, it has a slightly different decision boundary. Then the last bit is nearest prototype, and here I just implemented it so you can actually step through it. So nearest prototype, all it does is takes the mean of all the white dots, takes the mean of all the black dots, and then based on those two centroids or means, then it classifies a new point as whichever centroid it's closest to, that's the prediction. So if you're closer to the 0, the class, or in this case class A, if you're closest to the centroid that's class A, you get the label of A. And that's very, very easy to implement. So here we just take all our 100 subjects from class A and take the mean. So the centroid for class A is at negative 0.04, which is about right here, and then 1.5, which is about right here. So wherever my cursor is, that's the center of all the black dots. Makes sense. And then we do that for the other class. Look at the centroid there. So it's 2 and 2.1, so that's about where my cursor is. That makes sense. The mean of all the white dots is about there. And then we just reduced our entire data set to these two little points. And then all we have to do now is, for each grid point, remember we're evaluating on a 200-200 grid spanning this range, we're going to find the distance to centroid A. So we do a minus operation. If you remember, BSX fun automatically expands out the singleton dimension, so it takes 2 by 1 and makes it 2 by 40,000, because that's what the dimensionality of this thing is. Anyway, so for each point you take the difference along the x dimension and difference along the y dimension, you square, and then you sum across all of our dimensions, take the square root. So this is just Euclidean distance. Euclidean distance is x squared plus y squared plus z squared plus whatever squared, square rooted. So this computes the distance of all of our 40,000 points to centroid A. This computes the distance of all of our 40,000 points to centroid B. Then our last thing we do is this. So this says, on a element by element basis, if the distance to A is bigger than the distance to B, then we should classify as B. And according to our convention, B is 1. So this whole statement is true. We'll output 1 if we're closer to B. And then the converse of that, or the inverse of that, whatever. If you're closer to A, then you're going to get a value of 0. So then you just make your image and put up a contour and make it red. In this case, pretty substantially different decision boundary, and you can kind of eyeball it, although our space isn't equal. Remember, we're working with Euclidean distance, so the scaling of our x and y is very important. So now I made it such that equal pixels equal actual numbers. So 0 to 2 along the x is the same distance from 0 to 2 along the y. So now that we've made that true, you can kind of think about the centroid. So the centroid of black is around here, centroid of white is around here, and then the separating decision boundary is just perpendicular bisector, to use some geometry. But it's just, you join the two centroids and you plop out a hyperplane that's perpendicular to it. In this case, we're in 2 dimensions, so it's just a line. But in 3 dimensions, it'll actually be a plane that has extent, and then in 4 dimensions, it'll be a hyperplane, and it gets crazy beyond that, but that's basically what's happening. And we're done. We just put a legend. So all of our different types of classifiers gave rise to different decision boundaries, but they all basically do pretty well for this data set. And that's it.